In particular, we talk about LTI systems, linear time invariant systems, step response of such systems, impulse response, the relationship between the two, which will lead to ultimately to convolution. In the last lecture, we talked about upsampler and also downsampler as examples of digital systems. We also took a moving average system as an example, and we introduced the concept of linearity having two necessary and sufficient conditions, namely principle of homogeneity and principle of superposition. Then we talked about time invariance and time varying. We showed that an upsampler is a time varying system, so is a downsampler. There was a question about the shape of the waveform, so I would like to go through this example once more. What we took was x of n was this 1, 2, 3. These have not been drawn to scale, but you understand what I mean. This, when upsampled by L equal to 2, this is x of n and this is y of n. The result is that there is a sample at 0 of amplitude 1, then there is a 0 in between, it introduces 1 0, then we have the sample of height 2 at 2, then we have a 0, and then at 4 there is a sample of height 3. Okay. Now, if I delay this signal by one sample, then I start with a 0, then a signal of amplitude 1, next a signal of amplitude 2, and finally a signal of amplitude 3 at 3. This is x of n minus 1. And when this is upsampled by a factor of 2, what we have is 0, then another 0, then at 2 we have a signal of amplitude 1, okay. Then we have a 0 at 3, then at 4 we have a signal of amplitude 2, then a 0, and at 6 we have a signal of amplitude 3. Okay. It's a little involved concept, so you must understand where the trick is. And this is my y1 of n. Now, one of the comments was that the waveform, that is 1, 2, 3 with zeros in between, is preserved. Okay, waveform is preserved, but what about the delay? How many samples are this delayed by in comparison to this? 2 samples, whereas x of n minus 1 should have led to y of n minus 1. That is, if this was delayed by one sample, we would have agreed it is a time invariant system. This is not equal to y of n minus 1, and therefore it is a time varying system. So, waveform preservation is necessary, but not a sufficient condition for time invariance. Is the point clear? Not only waveform preservation, but the delay must be the same as the delay of the input, otherwise it is a time varying system. Is this okay? All right. Now, we also talked about causality, and we made a dig about astrologers, which you can ignore. But as far as electrical engineering systems are concerned, they cannot anticipate what will happen in future. However, non-causal DSP is also used in the case of recorded data. That is, the whole data is available, and therefore wherever you fix your n equal to 0 for negative values of n, this is also available, or for future values of n, the data is available, and therefore non-causal DSP can also be used and is used in several practical applications. One of the most common examples being geophysical data, geophysical signal processing. We talked about stability, and the kind of stability that we talked about was bounded input, bounded output. In other words, if the signal, input signal is bounded, so should be the output signal. If the output signal grows without bounds, then it is an unstable system. We introduced the concept of passivity and losslessness. We also commented that in digital systems, these are artificial concepts, just like energy. Energy of a signal is summation magnitude squared over all values of n. This is a definition of energy. It is not energy in the sense of analog systems or analog signals. Passivity we define if the output energy is less than or equal to the input energy, then we say the system is passive. You realize that a passive digital system can be made active just by multiplying it by an arbitrary number. We can always increase the energy by scalar multiplication. So, this is why this is an artificial concept introduced for the purpose of analysis and design. Similarly, when the output energy and the input energy are the same, we say the system is lossless. And we ended up the last lecture by taking an example of a system which is y of n equal to x of minus n, and we said that this system is linear, causal, yes, non-causal, right, linear, non-causal, it is stable, it is passive, and it is time varying. To show, we proved the time varying nature analytically. Let us take an example, very simple example. Let us say that our x of n is simply this signal 0 and 1, and the amplitudes are 1. Okay. Then y of n, which is x of minus n, will have a sample at 0 and at minus 1. Okay. So, this is y of n equal to x of minus n. Now, let us delay it by one sample, that is x of n minus 1, then it will be 0 here, 1 here, and 1 here. Okay. So, y1 of n would be 0 at 0, and then we shall have 1 at minus 1. This signal is simply folded back. So, another signal of amplitude 1 at minus 2. This is y1 of n, which is obviously not equal to y of n minus 1. Isn't that right? What is y of n minus 1? What does this signal look like? It is simply 1 at 0. This signal is delayed by one sample. So, it shifts to the right, and therefore, this is what it is. And don't you see that these two are identical, isn't it? Y of n minus 1 is the same as x of n. This is incidental, it does not have to, but you notice that y1 of n is not equal to y of n minus 1, and therefore, the system is time varying. I must also caution you that in many instances I take examples to convince you after analytical proof or without analytical proof to convince you the truth or falsity of a statement. May I also point out that 1,000,000 examples are not adequate to prove anything. You cannot prove anything by an example, all right, but you can disprove something by just one counter example. Okay? If I say here that everybody in this class is in the age range 22 to 30, okay, there may be one person who is 31 or 30.5. 30.5 age is permissible. Age is not a digital quantity, isn't that right? Number of years, you can be 30.5, all right. So, I repeat, when one is asked for a proof, no amount of examples will suffice. You have to prove it in general. Whereas for disproving, if you want to prove that a system is nonlinear, just apply any one of the principles, superposition or homogeneity. And the easiest one to do is to use which one? Homogeneity, not superposition. Just say 0 input, does it lead to 0 output? If it doesn't, then the system is nonlinear. You don't have to go further, okay? So, that's what it is. That y of n is equal to x of minus n is stable is obvious, because if x of n is bounded, y of n is bounded by the same quantity. Then we talk about impulse response and step response and the relationship between the two. The definition is very simple. You have a digital system, you apply a delta n to it. Your input is a delta n, and whatever the output is, we shall denote it by h of n. If h of n is 0 for n less than 0, then the system will be causal, because delta n comes at n equal to 0. If the system has an output before n equal to 0, it means the system is non-causal. All right. Similarly, when you, to the same system, same digital system, you apply u of n, the output is usually denoted by small s of n, that is the unit step response. The symbol small s is usually reserved for the analog complex frequency, and when there is a chance of confusion, we shall not use s of n to denote unit step response. When you talk about bilinear transformation, transformation from analog to digital or vice versa, we shall use some other symbol, but so long as we do not come to the bridge, we shall not cross it. We shall keep s of n as the unit step response. This is the definition. Let us take some examples. Now please pay attention, because some of these examples are a little tricky, although they look very simple. The first example that we take is that of an accumulator. You know, an accumulator can be of various types. Let us say the accumulator is y of n equals to summation x of L, L going from minus infinity to n. All right. It's an accumulator, accumulates data from minus infinity up to the present instant of time. Now, what do you think its h of n shall be? H of n. H of n means we shall have to substitute x by delta, and delta of L exists only for L equal to 0, and therefore this is 1 if n is greater than or equal to 0. Isn't that right? If n is less than 0, then delta of a negative number is identically equal to 0. Therefore, it is 0. Is the point clear? Now don't you see that this is precisely the definition of a unit step function, and therefore h of n is equal to u of n. Is this clear? Okay. Take another version of the accumulator. Suppose x of n equal to 0 up to infinity, that is all range of n. What would be its h of n? H of n would be simply k equal to 0 to infinity delta of n minus k. What is this signal? It's precisely u of n. This is precisely u of n. So although the definitions of the two accumulators are different, the impulse response is the same. Agreed? All right. Let's take a third example. Suppose we take the third description of an accumulator, that is y of n in terms of initial condition is y of minus 1 plus summation x of L going from 0 to n. What do you think its impulse response shall be? H of n. In the same manner, it would be y of minus 1 plus 1 if n is greater than or equal to 0. On the other hand, it is simply y of minus 1 if n is less than 0. All right? You know that this is a nonlinear system. This is a so nonlinear systems can also have an impulse response, but the other properties that we are going to discuss will not hold. Convolution, for example, will not hold for a nonlinear system in the form that we are going to present it. Let's take another example. My favorite example is that of a sampling rate converter. Okay, let's take an upsampler. Upsampler, as you know, is described by y of n equal to x of n by L, n equal to 0 plus minus L plus minus 2L and so on, and it is 0 otherwise. So its h of n would be simply equal to, yes, put x equal to delta here, delta of n by L exists only for n equal to 0. N equal to plus minus L would make delta of plus minus 1, which is 0, and therefore this is simply equal to delta n. H of n is simply equal to delta n. Suppose we find the impulse, the unit step response, S of n. Then what would be S of n? It would be, you have to substitute x by u. U of n by L is equal to 1 when n equal to 0 plus minus L plus L only, minus L, u of minus 1 is 0, and therefore this would be delta n plus delta n minus L. In between it shall have L minus 1 zeros plus delta n minus 2L and so on, which amounts to the fact that this is delta of n minus k, L, when now k goes from 0 to infinity. Agreed? So this is the impulse response. Although it is a time varying system, it has an impulse response, but it's a linear system, right? Upsampler. Similarly, you can show that a downsampler also has an impulse response, and I leave it to you to find out what its impulse response is. Suppose we have an interpolator. Next example. And a simplest interpolator is something like this. You take the present value and to it you add half of the immediate past and the future values, that is x of n minus 1 plus x of n plus 1. Obviously, this is a non-causal system because the present output depends on a future input. What would be its impulse response h of n? It would be simply delta n plus half delta n minus 1 plus delta n plus 1. And if I plot it, it shall have a sample of 1 at n equal to 0. At n equal to 1, it shall have a sample of half, and at n equal to minus 1, again it shall have a sample of amplitude half. Okay? This is what its impulse response looks like. It is interesting to find out what its unit step response would be. Unit step response S of n is equal to u of n plus half u of n minus 1 plus u of n plus 1. Okay? Let us see what this means. U of n is starts at n equal to 0 and its amplitude is 1 for all values of n. You have to add it to u of n minus 1 half, which means that this starts at n equal to 1 and the amplitude is half all through. This is half, this is 1, and then you add to half of u of n plus 1, which starts at n equal to minus 1, and therefore you have samples like this. All the rest are 0. Okay? All the rest on the left side are 0. This must be pointed out. If you add this, this is half. If you add this, then what is it that you get? At n equal to minus 1, this is where it starts. It will have a value of half. At n equal to 0, it shall have a value of half plus half 1 plus 1, which is 2. Then at n equal to 1, n equal to 0, I am sorry, I have made a mistake. U n plus 1, I made a mistake. It starts from here. Agreed? This is 0, so this is minus 1, and therefore I beg your pardon. The result would be at n equal to minus 1, it would be half, n equal to 0, it would be 1 plus 1, 2. That's okay? 1 plus half, 3 by 2. Okay? Very easy for me to change from 2 to 3 by 2, right? And then this is n equal to 1. Why did you say at n equal to 1 it is 3 by 2? N equal to 0 it is 3 by 2, agreed. Then at n equal to 1 it is 2, and it remains 2 ever after. Okay? So this is how one computes the unit step response. Now we talk about, we will not bring nonlinear systems or time varying systems. We talk about purely LTI systems. And very simple derivation of what is famous now as a convolution. You see, if the system has an impulse response h of n, that is if delta n leads to h of n, then delta of n minus k because of time invariance shall lead to h of n minus k. And if I multiply this by x of k, a constant, delta n minus k, then the output should be multiplied by the same constant, that is x of k h of n minus k. This is an example of the application of the principle of homogeneity. If the input is multiplied by xk, output shall be multiplied by xk. Then we apply the principle of superposition, that is, we sum this up, we apply all these inputs simultaneously, k going from minus infinity to plus infinity in general, then this should lead to xk h of n minus k, k going from minus infinity to plus infinity. But you see the left hand side is precisely x of n. An arbitrary x of n can always be expressed in this form. The output therefore must be equal to y of n, which is the famous convolution theorem. That is, for an LTI system, the output y of n is equal to summation x of k h of n minus k, k going from minus infinity to plus infinity. By changing the variable, by putting n minus k equal to r, you can easily show that this is also the same as k equal to minus infinity to plus infinity, x of n minus k h of k, and this summation, how do you prove this step? Put n minus k equal to some other variable r, and then you can show, finally you bring back k. Okay? This can be very easily proved. This is denoted by x of n star h of n. Star stands for convolution. In this particular context, if the star is written above a symbol, then it is complex conjugate. If star is written in the horizontal line, then it is convolution. And obviously, if these two summations are identical, then obviously the order of convolution is not important. In other words, this should be equal to h of n star x of n. In other words, convolution is commutative. The operation of convolution is commutative. Convolution is commutative. Now, there are some special cases that we shall encounter in practice. In general, our convolution is, mind you, this applies only to linear time invariant systems, because we have invoked in finding this summation the principles of homogeneity, principle of superposition, and also the fact that the input, if the input is delayed by a certain number of samples, k samples, then the output is delayed by the same number of samples. That is, we have also invoked time invariance. So, this is valid for LTI systems. If the system is time varying, then also we can write a convolution summation, but it would not be h of n minus k. This h shall now be a function to be found out of n and k, but the argument shall not be n minus k. So, for a time varying system, we write, instead of h n minus k, we write h n comma k. All right. We shall mostly be concerned with this system. Suppose the system, now we qualify the system, we consider some special cases. Suppose the digital system is causal. If it is causal, then h of n equal to 0 for n less than 0. That is, before the input is applied, delta n arrives, there cannot be an h of n. If that is so, then this argument will become negative when k exceeds n. Isn't that right? And therefore, the upper limit now should be restricted to small n. In the case of a causal system, therefore, the convolution summation simplifies to k equal to minus infinity to n x of k h of n minus k. You understand the logic, the reason. Beyond n, the argument of h becomes negative, which is 0. All right. Let us say that the input is also causal. Input is also causal, that is xk is 0 for k less than 0. If the system is causal and the input is also causal, then our special summation becomes k starts from 0 and goes up to n, x of k h of n minus k. In most cases, this is what we shall use, but there is no reason why to a causal system you cannot apply a non-causal signal. You can. We shall, in fact, in the examples that we take, we shall consider non-causal signal, but causal system. So this summation, let me take another. This is also black, let us take a green. This summation is valid for linear, time invariant, causal system LTIC. Okay? There is another qualification added, that is the causal system. This summation applies to linear, time invariant, causal system and signal, S and S. Okay, linear, time invariant, causal system. At given a situation, you must write the convolution summation correctly, otherwise you will get wrong results. We have already proved that convolution is commutative, that is x of n star h of n is the same as h of n star x of n. By applying the definition, you can very easily show that the convolution operation is also associative. That is, if you have, let us say, x1, I am omitting the argument n, if you have convolution of 3 quantities, let us say 3 signals, x1, x2, x3, then the order in which this is carried out is not important. In other words, it is the same as x1 star, x2 star, x3. You can first find the convolution of this and then convolve with the other one. Or you can also write x1 star x2 convolved with x3, associative property. The other property that convolution obeys, operation of convolution obeys, is the distributive property, which says that if you convolve x1 with x2 plus x3, then it is equal to x1 star x2 plus x1 star x3. It is the sum of the two. This is the distributive property, and the proofs, as I said, are extremely simple. Now, this summation y of n equal to summation k equal to minus infinity to plus infinity x of k h of n minus k obviously is a very simple operation, but in computing the convolution one has to be careful. the steps, if you want to do it step by step, I shall give you a trick later, but if you want to do it step by step, then you have to first find out what is x of k. Alright, x of k, you put down the signals starting with x0, you might have x of minus 1, you might have x1 and so on. Then for finding h of k, first the next step would be draw h of k, put these signals in their appropriate places, okay, with appropriate values of k below the x signal. Then find out h of minus k, which is simply taking 0 as the pivot, you flip it over. You take the right side to the left and the left side to the right. This is h of minus k. Then you find h of, let us say, 1 minus k. N varies from 0. You see, if you multiply the corresponding signals of xk, let me use it, xk and h of minus k, then you will get the value of y of 0. Then you find h of 1 minus k. What is h of 1 minus k? It is h of minus k shifted to the right by one sample. And if you multiply the corresponding signals, then you get y of 1. Similarly, you can find out y of minus 1 by multiplying xk signal by h of minus 1 minus k, which will mean a shift to the left by one sample, and you have to go on computing. Okay, let us take a simple example. Suppose k 0 minus 1 plus 1 2 minus 2. Okay, these are the values of k, and the signals are like this. There is a signal at, let me use a different color, the x signal. I will put the subscript where it occurs. Instead of x of n, I am writing x of x subscript n to conserve space. This is x0, x1, x2. Suppose this is my x of n, x of k now. Inside the summation I have x of k, h of n minus k. Then my h of k, to bring variety into experience, let us say h starts from here, minus 2, minus 1, h naught and h1. Suppose this is my h of k. I am taking two finite signals. Okay. Then h of minus k, let me change color, h of minus k, this will remain the same, h naught, and this will now be, this side will come to the right. So, it will be h of minus 1, h of minus 2 and h1 shall go here, alright, and therefore, concentrate now on these corresponding signals. Therefore, y of 0 shall be equal to x of minus 1 h1, the corresponding signals are multiplied, then plus x0 h0 plus x1 h of minus 1 plus x2 h of minus 2. There will be 4 terms, no other, because there is no other signal, okay? Neither signal nor the impulse response. Notice that the sum of the two subscripts is equal to the argument of y. This should always be the case. It is a running check. If you have a term here whose the subscript addition does not give the argument of y, then you have made a mistake. Okay. Our next task would be to find y1. So, we find h of 1 minus k. h of 1 minus k. Then we shift this signal by one sample. So, I get h of 1 here, this signal, then I get h naught, h of minus 1, okay, 0, 1, 2, then h of minus 2, I do not write it because the corresponding signal is 0, x is 0, agreed. So, I shift it till there is a overlap with x, I do not shift it beyond that, and now I can write y of 1, the corresponding signals, that is x0 h1 plus x1 h0, all right, plus x2 h of minus 1. Notice that the sum of the subscripts 0 plus 1, 1 plus 0, 2 plus minus 1 is again y of 1, right. If I want to construct y of minus 1, then I shall have to proceed like this. Let me write x signal first, minus 1, x0, x1, x2. The k values are 0, wanted to use some other, 0, 1, 2, minus 1, minus 2, okay. Then I require h of minus 1 minus k, and h of minus 1 minus k would be the same sequence shifted to the left. Now, what will be in this position? Yes, at the 0th position it would be h minus 1, agreed. H minus 1 comes here. So, this will be h of minus 2, and therefore, this will be h 0, and this would be h 1, agreed. So, my y of minus 1 shall be equal to this signal, there is no corresponding signal, there is no corresponding x. So, I did not have to write this, but anyway, since I have written h1 multiplied by 0 is 0, then x of minus 1 h naught, x 0 h minus 1 plus x1 h minus 2. Again notice that 0 plus minus 1 is minus 1, this summation of subscript is minus 1, this also gives minus 1, and you can construct, you can find out, compute all of them. You will notice that in total there are 7 non-zero samples of y. We shall have y0, y1, y2, y3. If we go beyond k equal to 3, then the impulse response goes out of the range of vision of x. You see, if I shift this, this is one sample, 2 samples h1 will come here, h0 will go here, 3 samples, I am sorry, this is one delay, 2 delays h1 h0, 3 delays h1 shall come here, and the 4th delay h1 shall go out of the range of vision of x. Similarly, on the left hand side we can go up to y of minus 1, y of minus 2 and y of minus 3. If we go beyond minus 3 to the left, then h goes out of vision of x, there is no overlap, and therefore the number of samples in y of n is equal to number of samples in y of n is equal to 7, and this is in general true. We have shown by one example, but it is in general true. In general, if the 2 signals which are being convolved have lengths of n1 and n2, if x1 has length n1, x2 has length n2, not necessarily 0 to n2 minus 1, it could have started at the in the left and gone to the right. Okay. Then y of n shall have n1 plus n2 minus 1 number of non-zero samples. This can be proved rigorously again by writing the summation. Just write the summation and show that beyond n1 plus n2 minus 1 there are no other samples, either to the left or to the right. Now the trick. Is there any question on this? Obviously this is a laborious process, and if you make a mistake you are done with. All future computations will be defective. Now a very simple trick that can be used, which does not use the graphical method, that is, you don't have to shift and multiply and compute and so on, is the following. What you do is, we write the signal x, x minus 1, x0, x1, x2. This was our signal, and the h of k, this is x of k, you write h of k below this at the corresponding positions. This is my k equal to 0, 1, 2, minus 1, minus 2, and my h was h minus 2, h minus 1, h naught and h1. Okay? This is what it is. And I multiply, you can show that the results are identical, but the trick, learn the trick. We multiply exactly like we multiply two arithmetic numbers. In two arithmetic numbers we bring them one under the other, but here you put them at their appropriate positions, put them in their places, then we shall see what we can do about it. And you multiply each of the upper row by each number in the lower row. That is, you put here h1 x2, h1 multiplies this, h1 x1, then h1 x0, then h1 x of minus 1. Agreed? Alright. What we have done is, we have taken h1 and multiply all these four numbers, put them in their appropriate places. Okay? Under x2, h1 x2, h1 x1, h0 x0. Where is h0? No, I am sorry, h1 x0 and then h1 x of minus 1. Agreed? In arithmetic addition, you leave a column blank, right? Do you know arithmetic addition? You have done it. Okay. So you leave a column blank, and then we take the next number, h naught. So we put h naught x2, then h naught x1, h naught x0, h naught x of minus 1. It has gone beyond, but does not matter, under minus 2. It has 2. Next one, I put another cross here, and I go like this, h minus 1 x2, h minus 1 x1. Pardon me? We don't reverse the sequence. We are writing hk as it is, no h of minus k, no confusion, h of k as it is, no modification. Alright. So h of minus 1, I forgot, x0, h of minus 1 x0, then h of minus 1 x of minus 1. Alright. Stop, because we have gone up to x, x of minus 1. The next row, the h of minus 2. So you take h of minus 2 x2, h of minus 2 x1, h minus 2 x0, and h minus 2 x of minus 1. Then you add. You add column by column. Please notice the interesting fact that this column, the sum is 3, and therefore the result of this column should be y3. Let me take a different color. Y3. The sum of this shall be y2. 0 plus 2, 1, 1. The sum of this shall be y1. This will be y0. This is your reference. In general, you shall not be given subscripts, you will be given only numbers. Okay? So you will have to, your pivot shall be where does h0 x0 occur? Well, h0 x0 occurs here. So this column must give me y0. And once I fix y0, next one is y1, y2, y3. Do you understand why I am saying this, the pivot? Because in a number there is no subscript. This will be, let us say, 2, 3, 5, 6. Now you do not know 6, that 6 is x2, you have to fix that. Where does the 0th sample, corresponding 0th sample come? That is your pivot. And then this is y of minus 1, y of minus 2, y of minus 3. There is nothing else on the right, nothing else on the left. And therefore we have got 7 signals, 7 output signals. And these are, if you compute the same by graphical convolution, compare with these sums, they are absolutely identical. And the logic behind this is extremely simple. You figure it out. But this is the trick I give to my students. They don't have to do this laborious page after page shifting computation and all that. Simple arithmetic multiplication with a little bit of constraint. There is no carryover here. In arithmetic multiplication there is a carryover, you add it to the next term and so on. No, you just multiply. Even if this number is 10,000, you don't take 1,000 out. No, you put here 10,000 and add them up. So this is a trick you must remember for the rest of your life, so that you can convolve two numbers, two sequences without tears or without sweat. All right. I'll just take one more topic, that is, if you interconnect two digital systems having impulse responses h1n and h2n, two or more systems, then obviously this is equivalent to, if you put an x of n here, this will be xn star h1, all right. If you put x of n here, then this output will be xn star h1n, and this output shall be xn star h1n star h2n. All right. So obviously this is equivalent to a single system whose impulse response is h of n, and h of n shall be equal to h1 of n star h2 of n. So in a cascaded system, the overall impulse response is the convolution of the individual impulse responses. Now a tricky question. Suppose one of these systems is unstable. Is it possible that the total system will be stable? No? It is not possible? Yes, it's possible. How? Pardon me?
So higher terms will be cancelled out while doing convolution.
Can you think in terms of poles and zeros? There may be a pole zero cancellation. If I take an example of an analog system, well, maybe I have a system S plus 2 divided by S minus 1, one of the systems. The other is S minus 1 divided by S plus 3. The product, this pole shall be unobservable because it cancels with the next one. So even if this system tends not to behave, the second system makes it behave. Okay? It does not allow the first system to go wild. Okay? But there are limitations. in digital systems there are limitations. For example, you must ensure that there is no saturation in any of them. If saturation occurs, of course, this total system shall be useless. Is there any question? Any question?